at University of South Dakota. Although Ryan just slightly missed the Nobel Physics Prize, he did share the breakthrough prize for fundamental physics in 2016. And today Ryan is going to talk to us about the nature of neutrinos.
Okay, I think I hear myself. So thank you, Dr. MacLellan, for this very generous introduction. In fact, I am at the University of South Dakota, but I have not bothered to update my PowerPoint template since 2012, so it still says Slack all over the place. I came up with this sort of outline for this talk when based on the abstract that I submitted, but as it turns out, in 20-25 minutes, I probably won't be able to motivate or convince you that neutrinos, in fact, should be Majorana particles, although I'll try to allude to a few reasons why as I go through the talk. One thing that I won't get into is an interesting consequence of neutrinos being Majorana. We could explain the baryon asymmetry of the universe via leptogenesis. So I'll mostly talk about the triumphs of EXO 200 and the fact that it is currently taking data, which is an achievement in and of itself, which I will address when I talk about the current status of EXO 200. And then I'd like to introduce you to NEXO, the obvious first choice for a ton-scale next-generation search. This is becoming a very important topic for us these days as we approach down-select for the next-generation neutrinoless double beta decay experiments in the US in, according to DOE, 2 to 3 years. But it's been 2 to 3 years for 2 to 3 years, so we're really pushing for 2017, 2018. So I was going to go into some details about beyond the standard model of particle physics, which I'll just call the standard model throughout this talk, in the neutrino sector. So the only evidence we have that the standard model is wrong, direct evidence, observed evidence, is in the neutrino sector with neutrino oscillations. So neutrino oscillations require neutrinos to have mass, and not only are they not predicted by the standard model of particle physics, the possibility of the neutrino having mass is actually excluded. So I won't get into the details of that today because I don't have time. Thanks to Ewan's wonderful introduction, I don't need to bring up the solar neutrino problem as a veiled attempt to point out that my supervisor, PhD supervisor, won the Nobel Prize last year. I can skip right to the results. I guess maybe even today, some current generation astrophysicists don't even talk about this solar neutrino problem since it has been resolved for quite some time now. But basically, neutrinos in the core of the sun are produced as electron neutrinos. We observe a deficit here at Earth as a result of them propagating in some linear combination of mass eigenstates between the sun and the Earth. There's some maximizing of the oscillation probability due to matter effects in the sun, but essentially you can write down the survival probability of electron neutrinos coming from the sun as the product of sine squared of a mixing angle in this unitary mixing matrix that allows you to convert between the flavor states and the mass eigenstates, and the difference between the mass squareds of for solar neutrinos, the first two mass eigenstates. And this is a function of the distance and the distance that the neutrinos propagate over and the energy of the neutrinos. So we can measure the energy of the neutrinos. Well, we can measure different energy electron neutrinos coming from different reactions in the sun. So we can span a large energy range, not so much distance with solar neutrinos. So we can actually put a good measurement on theta 1, 2. Short baseline or long baseline reactor neutrino oscillation experiments give us a good handle on the mass difference squared. We can make measurements of the difference, the mixing angle 2,3 and the mass difference 2,3 by looking at the oscillation of atmospheric neutrinos. So we have a good handle on a number of these parameters. But introducing neutrino mass and neutrino oscillations into the standard model of particle physics requires introducing at least 7 new free parameters into the model. This model started with 19 free parameters that describes all of particle physics up until this point. So this is a big extension. So this unitary mixing matrix that I introduced in the last slide, we call the PMNS matrix. It's kind of the analog to the quark CKM mixing matrix. Has 3 mixing angles between the 3 mass eigenstates, at least 1 CP violating phase. If the neutrino is Majorana, an additional 2 phases are possible. 2 mass difference squareds, and a minimum neutrino mass scale.
Could you just remind me what Majorana is again?
Oh, sorry. So Majorana.
Majorana.
So all fermions that we know of today are Dirac particles. The difference between Dirac and Majorana particles would be that the particle and the antiparticle are essentially the same particle, right? And so the only particle that can be a Majorana particle in the standard model is the neutrino because it has no charge. Okay? So equivalently, we could talk about 3 free parameters, the M1, M2, and M3 directly, but these are the things that we actually measure, and this is the thing we're interested in. So we typically talk about the minimum mass and the mass differences squared. So there have been attempts to measure the mass of the neutrino directly via endpoint measurements of beta decay spectrum. So you measure the energy of the beta coming out of beta decay, and that beta should have a maximum energy of the total energy available in the decay minus the mass of the neutrino. So neutrinos with, betas with energy in this range would, a neutrino emitted at the same time as a beta of this energy would essentially have no energy. The beta takes all the energy, but that's short of the endpoint energy by the mass of the neutrino. And so this is a very difficult measurement to make. This is 1 part in many orders of magnitude of all decays at this point. So up till now, the mass limits from beta decay measurements of tritium are something on the order of 2.2 electron volts. The next generation experiment, which has been trying to get underway for a number of years now, only hopes to get down by about a factor of 10 here on this limit, whereas cosmological, fits to cosmological data are already achieving mass limits on the order of the next generation beta decay measurements, albeit on the sum of the mass eigenstate masses as opposed to the neutrino, electron neutrino mass directly. And typically, in every talk about double beta decay or Majorana neutrinos, you get a picture of Majorana, but Majorana is also the name of the experiment we're sort of competing with for the next generation funding. So here's my picture of Planck. So if we put everything we know about neutrino mass into this picture here, we have three mass eigenstate neutrinos with differences between the masses squared. So we don't actually know which is which, depending on what the lower mass is. But we know that the difference between these two is something like 1/10 of a millielectron volt at most. And so the difference between these and the heaviest one would be something like 90 millielectron volts at most. So in the normal scheme, the difference between the mass difference between M2 and M3 is positive. We know the mass difference between M1 and 2 from the solar mass difference squared is positive due to the matter effects in the sun, but we don't know the sign of the mass difference between 2 and 3. So under what we call the normal hierarchy, nu3 is the heavier mass eigenstate, but equally probable, one would say, would be the inverted case where nu3 is lighter than nu2, and in that case we have the degenerate masses at the higher energy scale. So we also don't know the minimum energy. Depending on the hierarchy, this is either the mass of the first eigenstate or the third eigenstate, and that mass could actually still be 0. We don't know that. The color bars the colors on the bars represent the fraction of the flavor eigenstate that this mass eigenstate makes up. So the tau neutrino is more than 50% nu3. the electron neutrino is a very small amount of nu3, and mostly nu1. So this brings me to double beta decay, and in particular neutrinoless double beta decay. So double beta decay is a standard model process where you have two beta decays occurring simultaneously. For some even nuclei, such as xenon-136, these are somewhat lower energy configurations, so they can't single beta decay because it's energetically forbidden, but they can undergo two simultaneous beta decays. A beta decay is a weak process, so it's slow. Two of them, second order weak process, is extremely slow. So in fact, this decay hadn't been observed until EXO 200 came online in 2011, and the previous limit on this half-life we measured was incorrect. It's actually shorter than that. So I like to show that figure. So double beta decay, again, we just take two neutrons that beta decay. In this case, we have two W minuses emitted that decay to a anti-electron neutrino and an electron. So in this case, the neutrinos, just like regular beta decay, carry away some of the mass, some of the energy. The electrons end up with some continuous energy distribution made up of whatever energy is left in the decay. And so we usually can't distinguish between the two electrons, so we usually look for the sum of the two electron energies, and you see a nice beta decay spectrum from that. And just to point out, this has been observed for more than a handful of nuclei by now. Neutrinoless double beta decay is forbidden by the standard model because it violates lepton number conservation. This isn't that big of a stretch when you think about neutrinos, because neutrinos are also the only particles that violate lepton flavor conservation. You start with an electron neutrino coming from the sun, you can end up with a mu or tau neutrino in your detector at the Earth. So that's flavor violation, which is less rigorously conserved, I would say, than lepton number, but still. It's only an observed conservation quantity. It's not fundamental. In neutrinoless double beta decay, you have, again, at one vertex, the emission of an antineutrino, which somehow becomes a neutrino absorbed at the second vertex. So in effect, you have a source of Majorana neutrinos at one vertex and a detector of Majorana neutrinos at the second vertex. With this type of reaction, you have only electrons coming out. So if you sum the electron energy for this decay, you have to have the full energy available to the decay emitted in the electrons. You end up with a delta function at the maximum energy available to the decay. You apply some detector energy resolution, and this is sort of what it will look like. So often you'll see this type of plot where there's a very pessimistic insert that says that this peak is multiplied by many orders of magnitude just so you can see it on the plot. Well, this is actually our measured rate of 2 neutrino decay with EXO 200, and this is just below our sensitivity from our best measurement. So we could go down just from this several orders of magnitude where we have good separation between the double beta decay and the neutrinoless double beta decay. And this is not the best energy resolution we expect to achieve even with EXO 200. So again, I can't stress enough, the most important thing that we learned from this experiment is that the neutrino is a Majorana particle. This would be the only fundamental particle that is Majorana and has numerous implications, as I already alluded to. But we can also measure something related to neutrino mass from the decay rate of this reaction. This effective Majorana neutrino mass is some linear combination of the mass eigenstates weighted by the electron flavor content, right? Because what happens here is this is at both vertex in the standard model, we're emitting an electron neutrino, which is some combination of the three mass eigenstates. Nevertheless, we know what these matrix elements are, what these mixing matrix elements are based on neutrino oscillation measurements, so we can work out some information relative to the mass eigenstate masses. So if we take all this information and we put it on a plot, so this is the effective mass, effective Majorana mass as a function of the minimum mass eigenstate mass. So this is either nu1 in the normal case or nu3 in the inverted case. And so this is the allowed parameter space given the uncertainty on the phases in the mixing matrix, which are completely uncertain, and some additional uncertainty due to the uncertainty in the other parameters of the mixing matrix. So these are the errors on theta 1, 2, and delta m squared as measured by solar and atmospheric neutrino measurements and reactor-based measurements. So if in fact we're in the inverted case, the Majorana neutrino mass will be much higher, or could be much higher than in the normal case. The decay rate will be much faster, and we're more likely to measure, measuring neutrinos double beta decay will be easier. If the neutrino is not Majorana, this picture doesn't mean anything. So for the experiment that I choose to work with, we use xenon 136, and there's boilerplate reasons for choosing 136. The most interesting one and unique to xenon 136 is that we have the potential to tag the daughter barium nucleus using laser spectroscopy or something to that effect. If we can do this, we eliminate all backgrounds to the decay other than the 2 neutrino decay, which also produces barium 136. And so we're really the only experiment, if we can manage to achieve this, that doesn't have this third generic problem that requires other double beta decay isotopes to see double beta decay, neutrinos double beta decay. And that is that there might be an unknown gamma ray right at the Q value of your reaction where you expect to see your signal. So this brings me to the experiment we currently have running, EXO 200, which is a 200 kilogram scale experiment. We have approximately 175 liquefied kilograms of xenon, and we typically use about 100 kilograms of that as fiducial. So this is a very large collaboration. This picture was taken last summer. This is the actual detector that we have built, but you can't see it because it's all heavily shielded, so we usually show this cutaway schematic. The liquid xenon is housed inside a thin-walled copper vessel, and by thin I mean 1.4 millimeters, and this is about 40 centimeters in diameter by 40 centimeters in length. So this is thinner than a pop can, let's say, for the size of it. This is within about, let's say, 30 centimeters of cryogenic fluid, double-wall cryostat, 25 centimeters of lead, with 29 very large plastic scintillator cosmic ray veto panels surrounding this clean room that this is all housed in at a depth of 2,000 feet in salt mine. And by salt mine, I mean transuranic waste disposal facility. So we're located at the north end of the mine, and the nuclear waste is disposed in the south end of the mine. This is not a problem, except for the fact that, the radioactivity is not a problem. In fact, this particular site is low in uranium and thorium and radon in our area. The only problem comes when the host facility, WIP, really screws up and has a couple of accidents within a week, which, if I have time, I'll get to. So this is what our experiment looks like. We chose this particular collaborator as the shortest collaborator we have to make the experiment look that much more impressive. So you see the cosmic ray veto panels surrounding this clean room here. This is another clean room. The detector is somewhere in that room there. This is a picture of the vessel being inserted into the double-wall cryostat. So you see the inner wall and the outer wall. This is a laser guide. Never build a cryostat with a side-mounted door. It's a disaster to try and work with. Inside the vessel, we have dual time projection chambers that record dual energy signatures, ionization and scintillation. You need both of these in liquid xenon to achieve the maximum energy resolution performance. So we have, when energy is deposited in the liquid xenon, we get prompt scintillation light, which we collect with avalanche photodiodes at either end of the detector. We drift ionization electrons in an electric field to cross-wire grids at either end of the detector. So this is a central cathode with a TPC on either end, time projection chamber. So we use the position that we collect the signals on the wires to reconstruct an X and Y, and the time difference between the scintillation and ionization photons to reconstruct the Z position. So we can reconstruct not only single energy deposits, but multiple energy deposits, which is important because the single energy deposits are typically signal, and backgrounds are typically multiple energy deposits. So I'm going to skip through the details of the detector. This is sort of what a typical event will look like, a typical radon event in our detector. We see prompt beta followed by alpha decay sometime later. So the alpha emits a lot more scintillation light than the beta. The beta results in a lot more ionization collection than the alpha. So we have good discrimination between alpha and beta. The decays occur at the same position in X and Y, just separated by time. And if we introduce some radon, we can actually tag these bismuth poloniums quite efficiently, see the decay of radon in the detector down to some steady state level, which is typically about 1 per hour. Energy calibration, we'll skip through. So this is data from our most recent run. We published back in 2014 in Nature. So the details of this slide I'll skip over mostly. It's about 100 kilogram years worth of xenon-136 data. Thank you. This is a zoom in on the energy range around the Q value, and you see the best fit to the data with this purple being our fit to the zero neutrino double beta decay, and it's positive, but it's completely consistent with 0. The backgrounds in a region of interest total something like 31 for this data set. I personally did the calculation where we took all of the radioactivity we measured in all of the parts of the detector, put them into a Monte Carlo, and calculated what the number of background we would expect to see the detector should be before we even turn the thing on, and that was 30. So when we say we're going to achieve a background, we achieve a background. The same is true for the energy resolution, which I didn't get into. Not seeing any signal, we set a limit on the half-life, and this corresponds to some range of masses depending on which nuclear matrix element you happen to choose. Which brings me to our next generation experiment. Again, another large collaboration, mostly consisting of the same people with additions from EXO 200. We want to go to 5 tons. The worst thing we can do actually is to build a detector, or 40 detectors the size of EXO 200. The biggest power of a monolithic xenon detector is self-shielding. So this is our primary background, 2.5 MeV gamma ray. This is how far it travels in EXO 200. And in something that's 5 tons based on the same design as EXO 200. We don't expect any backgrounds in the xenon itself. It's a noble gas, so it's very easy to purify. So basically we expect all our backgrounds from the outside. In NEXO we expect very low background in the center of the detector. And so these are just conceptual designs of NEXO. Current sensitivity to the mass that we published 2 years ago now. This is a bit old. As far as we expect to get with EXO 200, with 5 years of NEXO, and then additional 5 years of NEXO if we start tagging the daughter barium ion and end up with 0 background. So well below this inverted hierarchy regime. And this is typically where next generation experiments are aiming. We could go lower, they could go lower, but we have to set some benchmark to compare what we can do for the next generation proposals. And I think I'll stop there.
Any questions for that?
Sure.
So is there a connection between all this neutrino physics and the Higgs field, or the dark matter search, or supersymmetry, or, what is the connection?
So there are lots of non-standard interactions that can mediate the neutrinos double beta decay. What I showed was just the exchange of light neutrinos. No matter how it proceeds, the neutrino has to be Majorana, but there are other non-standard reactions that can result in this. In terms of connection to the Higgs, so that's part of the motivation for why we think the neutrino should be Majorana, why theorists prefer that. In order to give the neutrino mass via the Higgs mechanism, it's much more favored that the neutrino be Majorana than Dirac. The reason being, there's a problem. There are 2 problems if you try and extend neutrino mass in the standard model via the standard Higgs mechanism straight, and that is you have to invent a right-handed neutrino that just doesn't interact, or interacts at like 10 to the minus 26 the strength of the regular neutrino, right? Because we don't see it. And also, the mass of neutrinos is something like 10 to the 8, a factor of 10 to the 8 less than the next lightest lepton, right? And so these are very hard to explain by giving neutrinos mass via the standard Higgs mechanism. But if they're Majorana, the Higgs mechanism via the seesaw works really nicely, explains the low mass, and the Higgs mechanism works for neutrinos much more nicely if the neutrino is Majorana. It's more natural, let's say.
Any other questions for Ryan? I'm just curious, did you detect anything around September 14, 2015?
No.
Okay, let's thank Ryan. Our next speaker is our Ewan O'Sullivan. Dr. O'Sullivan got his PhD from University of Birmingham in UK in 2002, and then he came to Center for Astrophysics as a postdoc and later astrophysicist. And he went back to UK during 2009 to 2011 as a Marie Curie Inter-European Fellow, and he did this in University of Birmingham. And after that, he came back to Center for Astrophysics, and now he's living a double life. Sometimes he's an astrophysicist in X-ray studies of galaxy groups, clusters, and early time galaxies. And most of his time he's working as a software developer, and he's currently working for the pollution monitoring mission Tempo. And today he's going to give us a overview of Tempo.
Thank you. So I'm going to talk about Tempo, which is an atmospheric pollution monitoring mission, which is going to be operating in geostationary orbit, looking down at North America in a few years' time. The mission is led by Kelly Chance, who is here with us right now in the AMP division, and his team. My involvement is with the ground systems. I'm working with John Houck and John Davis, who some of you will know from their work on Chandra down at MIT. And I see that we have several AMP scientists here, so if the science questions go beyond my knowledge, I'm sure they'll be able to help. So this is the kind of one-slide overview for the mission. The goal of Tempo is to provide hourly monitoring of pollution over greater North America. It's a UV visible spectrometer with a scan mirror in front of its slit so that it can scan that slit across North America once an hour, collecting spectra. The principal products are maps of the ozone, NO2 and formaldehyde column density through the atmosphere, and profiles of ozone tracing the ozone density down from the stratosphere all the way down to ground level. Resolution is about 2.5 by 5 kilometers. We have to bin up slightly for the ozone profile, but we're still pretty good. And it can actually measure a whole host of other pollutants in the atmosphere, SO2, bromide, glyoxal. It can measure water vapor, aerosols, all kinds of things. So, as I say, the PI, Kelly Chance, is here at SAO. We have some of the main algorithm developers here at SAO, and instrument operations and the data pipeline will be here once we get around towards launch. The instrument's being built by Ball Aerospace. NASA Langley Research Center is our project management group, and there are a whole host of other institutions involved: Goddard, NOAA, the EPA, Harvard. It's a pretty cheap mission. It's only $90 million, and our expected launch date is 2019 to 2021 right now. It's worth pointing out that the mission is it has a number of firsts associated with it. It's going to be the first mission of its type operating in geostationary orbit. It's the first of NASA's Earth Venture missions, which means that we're not flying on a NASA satellite or a NOAA satellite. The instrument will be attached to a commercial communications satellite. It has greatly improved temporal and spatial resolution over previous instruments of this type operating in orbit. And as I say, it's going to be monitoring ground level ozone below 2 kilometers, where it actually affects the population for the first time from orbit. So I thought it might help to outline the chemistry that leads us to be interested in these three products: ozone, NO2, and formaldehyde. So ozone, as we know, in the stratosphere is beneficial, forms the ozone layer, protects us from harmful UV. But once it's in the troposphere, below 10 kilometers, it's problematic, partly because it's a greenhouse gas, but also because once it's down at ground level, it's harmful to health. People with respiratory problems, people with asthma, young children, old people, it's not good for them to be breathing this stuff in, and it also damages plant life. The main source of ozone, or a main source of ozone at ground level, is photochemical smog, the stuff that builds up over cities in the summer. And that consists of nitrogen oxides, for which our tracer is NO2, but those include NO, NO2, and NO3, and volatile organic compounds, for which our tracer is formaldehyde. When those chemicals get together in the atmosphere and mix under sunlight, they produce ozone. Now, nitrogen oxides themselves are not wonderful things to be breathing in, and NO3, of course, is nitric acid, so it produces acid rain. They mostly come from combustion sources, so vehicles, power plants, large natural fires, that kind of thing. And then volatile organic compounds come from similar sources, but also from industrial processes, from oil and gas manufacture, and also the plants can produce these things. Trees under heat stress produce this chemical glyoxal, which then contributes to smog and breaks down to form formaldehyde. So if we can trace those three chemicals, we can get a handle on the ozone cycle in the atmosphere and keep track of these pollutants. Here's a map just showing you counties in the US violating ground level ozone standards. So you can see it's a fairly serious problem. These kind of measurements are mostly done from the ground at the moment, or perhaps from aircraft. But of course, you can't really tile the whole of the US with spectrometers looking up to measure the ozone density around them. So doing it from space is a much better option, provided you can get the spatial and temporal resolution. I'm not going to run through all of the science questions that are listed here, but just to point out a few things. There's the question of the contribution of these chemicals to climate change, and also the impact that climate change will have on pollution if you warm the atmosphere up. What's that going to do? We're going to be producing data which is good enough to go into air quality assessments and also air quality forecasts. So it would be great if our data can be used to predict for people when it's going to be good for them to go out. If you're a jogger who suffers from asthma, when are you going to be able to go out for a run? We will be able to look at this issue of intercontinental transport. So for people on the West Coast, pollution that blows over from China, or people in Europe, pollution that blows over from the East Coast. And there are also episodic events, wildfires, dust storms over the desert regions, volcanic eruptions. We'll be able to look at their impact on air quality as well. So, benefits of going to geostationary orbit. What you need to know beforehand is that the previous missions which have done this kind of work from orbit have been in low Earth orbits, sun-synchronous polar orbits, and they basically orbit about once an hour. On the day side, they collect data, and they build up maps of pollution over the whole surface of the Earth during the course of a day, but they only cover any given position once during that day. Now, obviously, things change in the atmosphere on timescales shorter than once a day. And this plot shows you a graph of the NO2 concentration in a model of the atmosphere over Houston, Texas. So it covers 2 days. The yellow blocks are daylight hours. And you can see at the start of each day, there's a big spike in NO2 concentrations, which is basically the morning rush hour. And the fact that the sun is low, and so the rate at which the atmosphere is cool, the rate at which this stuff reacts away is relatively slow. Unfortunately, OMI, the current instrument which is monitoring this kind of stuff, it passes over Houston sometime in the early afternoon, a little after 1:30, and it takes measurements right in the trough. You see those two red dots, and that's around lunchtime. Most of the pollution has died down, fewer people are on the roads. And so those measurements would suggest that the pollution is not too bad, but actually in the morning and evening, when people are experiencing it, it's much worse. So being able to measure this stuff through the day and not just once is pretty important. There's another example here. So this is a map of NO2 taken from an instrument called Geotaser, which is kind of a testbed instrument for TEMPO. It operates on an aircraft, and so this map's built up by flying the aircraft back and forth over Colorado. Blue is the kind of background level, and you can see enhanced pollution over Denver and extending out to the northeast. I should say that this data was built up by Caroline Nolan in AMP. Now, the thing about it is, this is the morning, and this is the afternoon, and you can see there's a pretty dramatic change between those two. Now, some of that is going to be changes in activity on the ground, but some of it is wind direction. So if you happen to be in Boulder, to the northwest there, you'd be pretty interested in knowing if the wind changes, how much pollution are we going to be picking up? TEMPO is going to be able to produce maps comparable to this, at least, over the whole US every day. Spatial resolution, as I said, TEMPO is going to be considerably better than the previous generation of instruments. This just shows you the pixel sizes for a couple of currently operating instruments and TEMPO over Washington, DC. So you can see that for OMI, the current generation instrument, that's not too bad. It breaks the city up into a few pixels. But for TEMPO, we're really tracing this down into particular suburbs. We can look at individual freeways, individual power plants. As I say, for most of our products, we'll be right down at the native pixel scale of the instrument, which is about 2 by 5 kilometers. And then for the ozone profile, we'll have to bin together 4 pixels. So you can see what 4 pixels bin together look like on that plot. That's still pretty good. That's the scale at which we'll be able to trace ground level ozone. This is what it looks like if you take Los Angeles and put the TEMPO pixel scale over it, which there's a lot of detail in there. And of course we do that every hour. So the instrument itself, as I said, it's a UV visible spectrograph. So we have our wavelength ranges there, 290 to 490 and 540 to 740 nanometers. Spectral resolution is about 0.6 nanometers, and we're using 2K by 1K CCDs. We'll be in geostationary orbit somewhere between 80 and 115 west, we hope. The ideal position would be about 100 west. And the field of regard is what's referred to as Greater North America. So from Mexico City or the Yucatan Peninsula in the south up to the Canadian oil sands in the north, which will be an interesting target to look at, and from the Atlantic to the Pacific. Instrument slit is aligned north-south, and the scan mirror sweeps it across once an hour, building up a data cube for us. And here's what that looks like if you were to take our measurements and extract data from them. So this is a map of NO2 being built up as the scan mirror sweeps across North America. You can see the East Coast, Midwest showing up nicely, California as well. The scan mirror takes about 1,300 steps an hour with about 3-second dwell time on each step. And that means that we're collecting 2.5 million spectra per hour. So our data rate's going to be something like 30 megabits a second, which means it's a good thing that we're going to be on a communications satellite. I will skip over this slide, which just gives you pixel scales for different locations. This is what spectra look like that we'll actually be collecting. So obviously it makes a big difference what is on the ground or in the air directly below us. The blue boxes show our UV and visible spectral windows. But you can see the red spectrum is if we're looking at clouds. We have high reflectance. We get a lot of the sun's light back to us. And you can see all those absorption features from the molecules that we're interested in. Deserts are pretty reflective in the optical window, and then ocean or vegetation scenes are less reflective. But if you look down on the bottom right, that pale green line, you can see it turning up above. The ocean spectrum, that's a vegetation feature which lets us look at what's on the ground, maybe look at the health of vegetation possibly. And having the UV and the visible is very important. Most previous missions have just focused on the UV, but the visible gives us a better handle on what's going on with the ground level ozone and also with clouds and aerosols. So, what's going on here at SAO? Well, as I say, the mission is led here from SAO. And a lot of the science algorithm development has gone on here. So there's a long history of developing these algorithms here at SAO for previous missions. It's worth pointing out, perhaps at this stage, that from an astronomy perspective, this is more like a survey instrument than a guest observer instrument. So most people will not probably want to look at the raw spectra. They will be more interested in the products that we produce from those spectra. And so that means that the algorithms we use to produce those products are one of the most important parts of the mission. Right now, there is work going on to improve the trace gas algorithm, which is used to measure NO2 and formaldehyde. That's been expanded over previous years to cover a whole host of gases, but work is still going on that. And in fact, publications are coming out right around now, I think. We are going to be able to separate tropospheric and stratospheric NO2. NO2 occurs naturally in the stratosphere, and obviously we want to be able to take that signal out so that we can look for the pollution lower down in the atmosphere. And work is going on the ozone profile algorithm to take advantage of this extra visible channel that we're going to have and make sure that we can actually trace ozone right the way down to the 0 to 2 kilometer level. Xiong Liu, who is here in the audience, is the developer for that algorithm, and he's done some work recently showing that that's definitely going to be feasible. The ground systems for the instrument will be here. In fact, our instrument operations center will be directly below my feet. Our office downstairs, D16, is where Tempo is going to be run from, at least in the current plan. It'll be staffed normal working hours, 5 days a week. It's important for this small mission that we should be able to operate autonomously and not have to keep people in 24 hours a day. We will carry out the usual kind of things, mission planning, which will be pretty simple since we only have 2 moving parts and we can't retarget anywhere else. We will have we will be building the command loads here, building 2-week loads and uploading those every week. We'll keep an eye on the health and status of the instrument, and we'll do some initial telemetry processing just to take the telemetry stream, clean it up, get it time ordered, and pass it on to the data processing pipeline. As I say, the data rate for this thing is pretty huge. So 2.5 million 2,000 element spectra per hour translates to 270 gigabytes of telemetry per day. And we want to be able to produce products, perhaps not right away, but within a couple of hours, let's say. So we need to be able to push this stuff through the pipeline pretty fast. Our current estimate is that we need something like 550 processors to do that, with about 2 gigabytes of RAM per core. That's actually not an unreasonable thing to ask for. We think that's about half a rack of equipment, so not really a big deal. The main science codes are written in Fortran. We've been doing some speed testing on those, and it looks like we are going to meet our expectations for those. This diagram just shows you a kind of simplified version of what our pipeline looks like. So we take in the telemetry, it comes down to the instrument operations, the IOC over there on the left, and it gets passed through to our level 0 to 1 processor, which takes the telemetry and converts that over into calibrated spectra. So radiant spectra, meaning spectra that we're actually taking looking at the ground, and irradiant spectra, which are our calibration data looking at the sun. Once we've done those, they get passed on to a code which looks at those spectra and retrieves the cloud pressure and the cloud... I've forgotten. Anyway. I'm sorry? Height, thank you. And once you have the clouds located, that information is passed on with the spectra to the main retrieval codes, which pull out NO2, formaldehyde, total ozone columns through the atmosphere, and the ozone profile code, which is going to be the most processor intensive of the codes. That will take up most of those 500 cores, but it's also perhaps our most interesting product. The main codes marked in the green box there in the center, those are all adapted from the previous satellite, OMI, and those are pretty much up and ready to go right now. The ozone profile code needs a little bit of work. The level 0 to 1 processor we still have to write, although we have it fairly well specified at this point. And once we've pulled out these products, They get passed on to our level 2 to 3 processing, which basically stitches this data together into maps covering the whole of North America. And if we want to, we can do things like daily, weekly, monthly averaging. The archive will be here, as will some of the data access for users. Let me talk a little bit about that. So our archive growth rate is something like 1 terabyte per day, building up to about 750 terabytes for the nominal 29-month mission. And at the moment, we're thinking we'll use NetApps to store that reliably. Again, we don't think that's going to be a problem in terms of getting hold of the equipment or keeping it down to a manageable size. Our off-site archive is going to be at NASA's Atmospheric Sciences Data Center at Langley in Virginia. They will store all of the data for the mission, and in fact all the software as well. Once the mission closes down, everything that we produce will be available to whoever needs it for the next instrument or mission. Our file format I thought I would mention is HDF5, which I've seen people are starting to think about using for astronomy data as well. It has the advantage that it supports very high dimensionality in the data. So we have a lot of data which has 3- and 4-dimensional arrays in it. And in fact, in some cases, I think 5-dimensional arrays. And HDF supports that quite naturally. It has a long heritage in Earth observation science, and it's actually pretty straightforward to work with. Data access for users. We will provide a website here at SAO for which people can get hold of the last 30 days worth of data. ASDC will provide a full archive, letting people download whatever they want. And then we're going to be making use of the EPA's Remote Sensing Information Gateway, which is kind of a virtual observatory style tool, which lets you look at data from a lot of different sources, compare that, subset it, visualize it in different ways, and only then download what you actually want. Now, that's actually an important capability for this. I was trying to figure out what a minimal data set would be and what it would take to download it. If you imagine trying to get measurements of NO2 for one position on the Earth for a month's worth of data, that's 144 gigabytes of data to download. If you want to do it for a year for the whole of North America, you can think about the scaling. It becomes difficult fairly quickly. So being able to subset stuff and only download what you need, that's an important capability. So we are currently on schedule and on budget, which is nice to be able to say. The instrument passed its critical design review in June and is now well on the way to being built. Ground systems, we have our own critical design review coming up at the start of May, which we are all busily preparing for right now. We are due to have the software ready and tested by the end of 2017. Thank you. Ground systems are supposed to be ready 6 months before launch. Instrument has to be delivered in the middle of 2017. And originally it was hoped that we would have a host selected by them, but it's now looking like we won't. Host selection will take place sometime in 2017. And only then will we know exactly which longitude we're operating at and what our launch date will be. But at the moment, the prediction is it will be somewhere between the end of 2018 and 2021. That actually works out fairly well because we are not the only people who are going to be operating this kind of instrument. ESA is launching a satellite called Sentinel-4, which will have a similar instrument on board, looking down at Europe and Western Asia, little bits of North Africa. And the Koreans are building an instrument, in fact they're building an instrument very similar to us, it's being built by Ball Aerospace as well, called GEMS, which is going to look at Eastern Asia and the Western Pacific. And you can see from the launch dates that we're going to fit in nicely with that constellation. So we hope that all three instruments will be up and operating for a good long while at the same time, so that we can compare data for different regions, and we can look at this question of intercontinental transport with pollution being moved around between these different zones. And I will finish there. Thank you.
There seem to be some issues about the launch vehicle and the readiness of the instrument versus somebody willing to manifest the spot to launch or something? How's that all going to play out?
My understanding, which may not be entirely correct, but Kelly can correct me if I'm wrong. My understanding is that because it's going up on a commercial satellite, they want to know for sure that we will be ready. They don't want to get into a situation where they have their launch lined up and we're saying, well, we're not quite sure yet. So their attitude, I think, is that they want to see the instrument actually delivered well in advance of when the launch is going to be. They want to know that they can just go and pull it out of a warehouse and bolt it on and not have to worry about us getting it done. So I think that's probably what delayed us.
Do you have another question?
You say the nominal mission is 29 months, I think you said.
Mm-hmm.
How much longer could it go?
As I understand it, it can just keep going indefinitely. It's a very simple instrument. The only moving parts are the scan mirror, and we have a filter wheel that is normally open when we're looking at the Earth, but it has diffusers to let us look at the sun. There's no consumables, so as long as those last, we can keep going.
Is there any other question? If not, let's thank all our speakers.
Very clear talk, very nice stuff.
That was excellent.
I have to.
You're lucky that you have satellite uplink. Our experiments in the desert,
Yeah.
we take 1 to 100 gigabytes of data a day. We put it on a hard drive, we give it to FedEx and ship it to California.
We've been talking about the question of how we get our stuff to from here to the archives up in Langley.
It might be faster to ship.
It might be faster, yeah. It's crazy, but it's true.
Since it's a satellite, can it fly to North Pole, South Pole too? So there's a pollution.
So we are fixed, right? We can't move around. But at the same time that we operate, there are already satellites that cover the poles every day, and
Sorry.
so the European mission equivalent to us, they have one satellite, Sentinel-5, anyway, which is doing the same kind of work we're doing. But then they have another one, Sentinel-4P, which is another one of these polar orbiting ones. So it covers the Arctic and the Antarctic every day, at least while there's daylight. So the data's there. I think the whole field started out from people looking at the ozone hole over the Antarctic, and then they realised that actually they could trace more of that interesting stuff as well. So.
That probably, the poles probably don't change that much over the course of the day anyway, so
No, you would. There's
that's
not
probably
exactly.
sufficient to
Just
just
sit
cast
back over here. Take your time. I'll let you get established.
Thanks.
That's still on.